My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, which is presented in two parts, I will begin discussing processes. I will introduce the process model, discuss the type of information associated with a process, give an overview of process state, and introduce the concept of process forking. As is usually the case, my presentation is focused on Unix-like systems. Let's begin by defining what a process is. A process is an instance of a computer program in execution. When we ask a computer system to run a program, the code for that program is loaded from disk into memory and executed as a process in the system. On some platforms, processes might be called jobs or tasks. On a modern system, a process consists of one or more threads of execution. In other words, a process can execute one instruction at a time, or it can execute several instructions at the same time on the CPU. Each process on the system receives its own private allocation of resources. Each process also has access to its own data, and the operating system maintains statistics about each process in order to make effective scheduling decisions. In memory, a process is divided into segments. Program code and other read-only data are placed into the text segment. Global variables in a program have their own data segment that allows both reading and writing. Automatic variables, or local variables and functions, are allocated at compile time and placed on the stack. Data structures explicitly allocated at runtime are placed on the heap. As memory is used by a process, the stack and the heap grow toward each other. If a process makes use of shared libraries, these libraries are mapped into process memory between the stack and the heap. In order to track processes correctly and allow multiple processes to share the same system, the operating system must track some information that is associated with each process. This information includes the memory that the process is using, as well as the current location in the process code that is executing, known as the process program counter. The operating system must also track other resources in use by a process, including which files are currently open and any network connections the process is using. In addition to the information generated by the process itself, the operating system must keep scheduling information and statistics about each process. This information includes a unique identifier, or process ID, that can be used to distinguish processes from each other. In order to arbitrate access to system resources, the operating system must also store information about the owner of a process so that permissions can be enforced correctly. To facilitate scheduling decisions, the operating system collects various statistics about process execution, such as the amount of CPU time consumed and the amount of memory used. During the lifetime of a process, the process moves between several states. When a process is first created, it is initially in the new state. Once creation is complete and the process is ready to run, it transitions to the ready state where it waits to be assigned to a CPU core. When the scheduler selects a ready process to run, that process is moved to the running state and is given CPU resources. During execution, a process might request external resources, such as disk I/O. Since these resources take time to provide, the process is moved out of the running state and into the waiting state so that the CPU core can be given to another process. Finally, when a process is finished, it is placed in the terminated state so that the operating system can perform cleanup tasks before destroying the process instance completely. In this diagram, we can see how processes may transition between states. At creation time, a process is placed into the new state while the operating system allocates initial memory and other resources. Once creation is complete, the process is admitted to the system and placed in the ready state. Whenever a CPU core is available to execute a process, it is dispatched to the running state where it executes. Execution of a process can be interrupted for a variety of reasons. If a hardware interrupt occurs, the operating system might have to move the process off the CPU core in order to service the interrupt. returning the process to the ready state. Or the process might make an I/O request, in which case the process is moved to the waiting state while the system waits on the relatively slow I/O device to provide the requested data. Once I/O is complete, the process is moved back to the ready state so that it can be scheduled to run again whenever a CPU core becomes free. Upon exiting, the process is moved to the terminated state for cleanup. The mechanism for process creation is platform dependent. I will be introducing process creation on a Unix-like platform such as Linux or Mac OS X. On these platforms, all processes descend from a single parent process that is created by the kernel at boot time. On Linux, this first process is called init, which is the common Unix name for the first created process. Apple decided to call this process LaunchD on Mac OS X. By convention, the initial process always has a process ID of 1. The initial process must also remain alive for the entire time the system is up and running, otherwise the whole computer crashes with a kernel panic. The init or LaunchD process is started by the kernel at boot time. Every other process on the system is a child of this special process. Child processes on Unix are created by forking a parent process. The parent process makes a system call named fork, which makes a copy of the parent process. This copy, which is initially a clone of the parent, is called the child process. It is up to the parent process to determine what, if any, resources it will share with the child process. By default, the parent process shares any open file descriptors, network connections, and other resources apart from the CPU and memory with the child. However, the program code can close or reassign resources in the child, making the child completely independent of the parent. Once a child process is forked, the child becomes an independent instance of the program, which can be scheduled to run in parallel with the parent. However, the parent process can be coded to wait on the child process to finish executing before the parent proceeds. Furthermore, the parent process is able to terminate the child process at any time. On some systems, termination of the parent process will terminate all child processes automatically. On other systems, child processes become orphan processes whenever the parent terminates. Unix-like systems, including Linux, have the ability to support both models. Any process, including a child process, has the ability to load a different program into its memory space. This loading is accomplished via the exec system call, which replaces the entire program code of the process with the program code from a different program. New programs on Unix-like systems are started by forking an existing program, then execing the new program in the child process. When multiple processes are executing on the same system, they have the ability to execute independently or share information between themselves. An independent process is completely separate from other processes in the system. Its execution is not affected by other processes, and it cannot affect other processes as long as the operating system is designed and implemented correctly. Alternatively, processes can share information between themselves and thereby affect each other. When this occurs, we say that the processes are cooperating. Cooperating processes may be used for a variety of reasons, including information sharing, implementing high-performance parallel computation, increasing the modularity of a program implementation, or simply for convenience when implementing certain designs. In Part 2 of this lecture, I will provide additional detail about process forking and executing new programs.